Do you use objects like this to hold papers on the refrigerator at home? Have you ever used a compass? Maybe you've noticed how your freezer door tightly seals itself. And you've probably used electric motors in things like toy trains and electric appliances. If you've used any of the things just mentioned, you've used devices made of magnets or electromagnets. During the next few minutes, we're going to explore some of the characteristics of magnetism and electromagnetism, and investigate some of the ways they make our lives easier. If you've ever played with magnets, you know that they stick together and attract some metal objects which contain a specific type of material. You decide, what is this material? It's iron. A magnet is a material which attracts iron or materials containing iron. Magnets are also capable of attracting other materials, such as nickel. Magnets don't attract materials such as wood, plastic, or glass. Magnets also exhibit certain characteristics. For example, a magnet has two ends where its magnetic effects are strongest. The ends of a magnet are called poles. One pole is called the North Pole, and the other is called the South Pole. If left to freely float, the North Pole of the magnet will point in a northerly direction. Magnets come in different sizes and shapes, too. For example, this is a bar magnet, and this is a horseshoe magnet. When you bring two magnets together, they exert a force on each other. They can either attract each other or push each other away. This attraction and repulsion are referred to as magnetic forces. Notice what happens when the north pole of one magnet is brought near the south pole of another magnet. They're attracted to each other. You predict. What will happen when the north pole of this magnet is brought near the north pole of another magnet? As you can see, the magnets repel each other. The same holds true when two south poles are brought near one another. The rule for magnetic poles is like poles repel each other and unlike poles attract each other. Each magnet is also surrounded by an invisible force called a magnetic field, which exerts a force on magnetic materials near it. The lines on this diagram illustrate the shape of the magnetic field around a bar magnet. Watch what happens when we hold this magnet below a piece of plastic on which particles of iron are sprinkled. Notice how the iron particles outline the magnetic field. This container houses a magnet which is surrounded with iron filings. Notice how the filings encompass the entire magnet, illustrating the fact that magnetic fields are three-dimensional. You may not realize it, but we live on a giant magnet. Just as this bar magnet is surrounded by a magnetic field, Earth is surrounded by an immense magnetic field. This magnetic field is strongest near the Earth's poles. Earth's magnetic field also extends outward through the atmosphere and into space. The magnetosphere is the region around Earth where magnetic fields are located. This diagram illustrates the magnetic lines of force in the magnetosphere. As we'll discuss later, magnetic fields can affect the motion of charged particles. The magnetosphere protects Earth from the continual flow of charged particles coming from the Sun. These streaming particles are referred to as solar wind. Occasionally, large volumes of charged particles do enter the magnetosphere, causing the air to glow in a magnificent display of lights referred to as an aurora. The aurora in the northern hemisphere is referred to as the aurora borealis, or northern lights. Another way we can see that the Earth has a magnetic field is because of the way this instrument, called a compass, reacts to it. A compass is an instrument with a magnetized needle that's able to rotate. The compass needle points north. For this reason, compasses are helpful in guiding people in the right direction, especially if they're lost in the wilderness. Whenever you turn on a light, use a computer, or dry your hair with a blow dryer, you're using energy which magnets helped create. You decide. What is this type of energy? It's electricity. Did you know that electricity and magnetism are very closely related? Believe it or not, electricity can make magnetism, and magnetism can make electricity. Nearly 200 years ago, scientists first observed the interaction between magnets and electricity when they noticed that a compass needle moves when an electric current comes close to it. Scientists concluded that electric currents produce magnetic fields. They also found that if a wire is twisted into many loops, called a solenoid, the magnetic force produced becomes greater. This nail contains a high concentration of iron. When we wrap a wire around a nail, forming many coils, and then pass an electric current through the wire, an amazing thing happens. The nail develops powerful magnetic properties. This is called an electromagnet. An electromagnet consists of a solenoid with the magnetic material, such as iron, inside it. Some electromagnets, such as the one attached to this piece of machinery, are so strong they can lift large pieces of metal. This electromagnet is very useful in this scrapyard. We just saw how electricity can produce a magnetic field and an electromagnet. But is it possible for a magnet to produce electricity? Amazingly, it is. This instrument is called a galvanometer. When connected to wires, it measures electrical current. You observe. What happens to the needle on the galvanometer as we quickly pass a magnet into the solenoid? As you can see, the needle moves, indicating that an electric current is produced. Electromagnetic induction is the process of generating an electric current. This happens when a conductor, such as a wire, passes through a magnetic field, in this case, the bar magnet. Electromagnetic induction plays a very important role in generating the electricity we use in our homes. This device, called a generator, uses magnets and conductors to produce electricity. Generators convert mechanical energy into electrical energy. Generators produce electricity used to light our homes and operate a wide range of electrical devices, from refrigerators to power tools to amusement park rides. Inside this generator are many large magnets which are spinning at a very high rate of speed. The spinning magnets induce an electrical charge on the surrounding wire, and electricity is produced. You may be wondering what force is responsible for spinning the magnets. Well, in this case, water contained by this dam is diverted across a turbine, causing the magnets to spin. Other sources of fuel, such as coal and nuclear power, are used to heat water to produce superheated steam. More environmentally friendly sources of energy, such as wind and geothermal power, are increasingly being used as alternative energy sources. During the past few minutes, we've explored the fascinating topic of magnets and electromagnets. We began by discussing some of the characteristics of magnets, including their ability to attract objects containing iron, and the ability of magnets to create invisible fields of force, called magnetic fields. We also saw how Earth possesses a magnetic field, which influences devices such as compasses, and also plays a role in the formation of auroras. Electrical current has the ability to form magnetic fields. In turn, when a wire containing current is coiled around an object containing iron, an electromagnet is formed. The amazing ability of magnets to create electricity was demonstrated, as was the ability of generators to convert mechanical energy into electrical energy through the use of magnets and conductors. So, the next time you use a magnet, use a compass, or use some electricity, think about some of the things we've discussed during the past few minutes. You just might think about magnetism and electromagnetism a little differently. Fill in the correct word to complete the sentence. Good luck, and let's get started. Number 1. A magnet attracts materials containing. Number 2. A magnetic is an invisible force surrounding a magnet. Number 3. This instrument is called a. Number 4. Induction is the process by which current is produced when a conductor changes a magnetic field. And number 5. A converts mechanical energy into electrical energy.